is organized by the IEEE GRSS student branch in Budapest. I'm Zsófia Kugler, and I'm going to be the host of today's talk, and we have a very special guest, Dr. Gudipati from NASA's Jet Propulsion Laboratory. So very warm welcome. Thank you for joining us. And he's going to talk about the Europa Clipper Mission today. This event is live broadcasted, so for those who are watching online, please make sure that your microphone is muted and your camera is switched off. But before starting, I would like to express our gratitude to the sponsors who made this event come true. So thank you for the US Embassy Science Fellowship Program, who enabled Dr. Gudipati to come to Hungary. And after the lecture, we are going to have an extended Q&A session. And for those who would like to post an online question, please do that in the chat box and don't unmute your microphone. And finally, before we kick off, I would like to share with you some thoughts about Gudipati's background. So he received his PhD in 1987 at the Indian Institute of Science in Bangalore, India. And after 3 years of a postdoctoral collaboration with Professor Joseph Michel at Austin, Texas, he joined the University of Cologne, Germany in 1990, where he was awarded the Habilitation of Physical Chemistry. In 2007, Dr. Gudipati joined the NASA's Jet Propulsion Laboratory, where he studies the evolution of ices in our universe. And Dr. Gudipati is actively involved in the Europa Clipper Mission as a co-I and investigation scientist. So Dr. Gudipati, the floor is yours. Thank you for accepting our invitation and hope we will have a successful event. Thank you.
Thank you, Zsófia. And also I met with the JPL, so it was a very nice meeting. And the US Embassy has put an enormous amount of work in bringing me here, especially Tibor. Thank you so much. And let's see, what is it doing right now? Extended mirror display. Let's see that. Okay, good. Good. Now we are good. Do you see that? No, you don't see that. Okay. Now you see it. Okay. You can put a couple of books there. That's good. I think it's good enough. Or yeah. Yeah, I'll be showing some videos probably. If you can close the curtains, that would be nice. Can you find out whether everyone can hear me online? If they can express, yeah, that would be good. I think, yeah, that's good. Okay, today's talk will be something entirely different from what you are used to. I'm told that you are at an engineering college here, university. I'm not sharing it. Okay. Let us see. Why is it not sharing? Escape. Good. Okay, now. Okay, now let's see. Sorry, we have technical issues, but it will be okay. Share. Okay. Yep. And then let me see. I will do this one. And then you have to select it. Yeah. No, not other teams. Other teams. Yeah. Here, and
you have to pick
yeah.
which one is.
I
think
no,
if
no.
you, oh, screen, yeah,
This
screen
is better. Yeah.
yes.
Okay.
And you have to.
No, it's good.
Okay.
Yeah. I think everyone can hear now.
Yes.
Yeah. I can go into the mode.
Presentation.
Yeah, that's good. Yes, that's what we have, right?
No, that's not good.
Not good? What are you seeing now?
Switch.
Oh, I see. Switch somewhere. Display, mirror display is not good. There's somewhere here, change the.
Yes, maybe this one. Swap this way.
Yes, exactly. Perfect.
Okay.
There we go. Technology works. It used to be never working, but it is working now. Yeah, so today I will be taking you to something that, though you're not learning in your day-to-day life, I'm sure that all of you have asked or will be asking these questions. Is it not going? It's going, okay. So you will be asking these questions, and we all, one day or other, wanted to know, are we alone here? On Earth, we have excellent biodiversity. Life is, really flourishing on Earth. But are we alone in our solar system? Are we alone in the universe? And this is a question that we all ask. And also we ask, where do we come from? What was the cause for humans to inhabit this planet? Where did it start from? So all these questions we ask, and sometimes we get answers, and sometimes we don't get answers, but we still go on asking these questions. And everything we do, one day or other, is connected to this kind of, very basic questions we have. And NASA's vision is also engulfed in these kind of basic questions. How did life happen here? Is there life elsewhere? What was the beginning and where we are going to? Because that way we know our place on this Earth, in the solar system, and in the universe. And everything that we do, one way or other, is connected to, is there life somewhere else? Or can life on Earth be there somewhere? For example, Mars, lunar to Mars missions to send humans, can humans survive there? And these are the questions that we ask all the time beyond Earth. One of the reasons why we need to ask this question beyond Earth, what is there, is it puts Earth and us in the context rather than in isolation. And that is the knowledge that we have been getting over the past several, let's say, hundreds of years. And so today's story is search for life in our solar system. You see that? No. Okay. And the context of Europa, why we are going to Europa. And as you go through, you slowly understand where I'm coming from and what would be the reason why we do what we do. So habitability is one word I want you to think about, keep in your mind. Habitability is the ability to provide conditions for life to start, to evolve and thrive. So Earth is a habitable planet. We all know that because we have biodiversity and we have, human beings also on that. Consciously, we know that. And are there other systems, planets, moons, whatever you want to see, in our solar system that are also habitable? And that's one of the questions that we ask. And in order to answer those questions, we need to understand what life needs. And basic things that life needs are light or energy, water, because all the biological systems need water or consist of water, and minerals that have interaction with biological systems. And then we also need the organic matter that makes all of us and every living being. So organic matter, minerals, energy, and water. So what we do is we follow water and see where else we can find that water in our solar system. In addition to all these four conditions that I talked about, there is one more or two more things that we need to keep in mind. Our Earth protects us from very harsh solar radiation. Sunlight is not only in the visible, where we can all actually, we need that, all the plants need that, but also it has very high energy infrared, the UV light, X-ray light, and also solar wind, which is a lot of electrons and protons. So Earth's atmosphere protects us from all those things. And that is the reason why for life to happen, you also need protecting from harsh environment and enabling an environment where the life can proliferate or succeed to happen. And one final thing that is needed, this is an entirely different talk, but Earth has given these kind of conditions to life since 4 billion years. Earth has been more or less habitable for last 4 billion years. So you need a long time period where life can happen and succeed. Otherwise, what happens is there could have been life very short period of time, and then the conditions were not good anymore. Maybe perhaps on the surface of Mars right now. That kind of things also play an important role. How long a body or a planet is life habitable? And these are things that we need to look into. I think I don't want to go in very much detail, but these are all the photographs or videos that I took. Just walking around, you have groundhogs, you have woodpeckers, we have butterflies, birds, and name it, biodiversity is beautiful. And I'll tell you, at the end of this talk, you will realize how unique the Earth and life here is, and how important to protect it. Only then, now, from Earth, as we started looking beyond, we asked the question, is there life somewhere else? A lot of times people assumed a lot of things or believed in a lot of things. But when we look into what is there and what is not there, we looked into our solar system, and so far we have not found any signs of life. And we are looking beyond our solar system. We are also looking into exoplanets right now, extrasolar planets. And we still do not have a concrete evidence for existence of any kind of life anywhere else in the universe. It doesn't mean that there's no life. The only issue is, how do we communicate? How do we find out? How do we test it? How do we remote sense it? Or how do we go in situ and look into it? These are the questions that are very difficult for us right now. So far, we have not been able to find life elsewhere else. That means we need to even give more care in protecting life here. Is it okay? Are we good? Good. So that's the reason why we have been at NASA looking for where else can we find at least habitable environments, leave alone finding life. Of course, going to Mars now, sampling Mars is trying to find out whether there is any trace of life there, or trace any evidence for life in the past. We are going beyond Mars and asking questions, where else are habitable environments? And one of them, as I said before, is to follow water. So water is essential for life. So we look for where else is water in our own solar system. And you see that we have identified a few bodies. Beyond Earth, most of the other bodies that we have identified are moons, either the moons of Jupiter or moons of Saturn. And among them comes Europa as the highest potential candidate that can be habitable. Okay, and I will get into why it is and why this is one of the reasons why we have this NASA flagship mission that is going to Europa and to investigate its habitability. Very interestingly, the whole amount of water that we have on Earth is only 1/2 of the water that is there on Europa. And on the surface of Europa, it is in the form of ice. So very cold ice. It's about 120 Kelvin to 60 Kelvin. So if you look into the temperatures, if you look into Celsius, 120 Kelvin is minus 153 Celsius. And 60 Kelvin is minus 193 Celsius. Oh no, 160 is 210, minus 210 Celsius. Okay, it's really, really, really cold. And at that cold temperatures, ice is harder than concrete. Okay, because your engineers, you will know the hardness of material, right? And to drill through that would be not easy, right? On Earth, drilling through ice is no problem at all, but there it is very difficult. Okay, so there's a lot of water on Europa. That's it. So we found one condition that is important for habitability. Now I'll tell you a bit more about Europa. I think it is in 1610, Galileo Galilei has discovered Europa. And today you can easily see using a small telescope like what I have here, or you can use even a camera with a zoom lens, and you can see all the 4 big moons of Jupiter: Io, Europa, Ganymede, and Callisto. When Galileo saw this and published it, he revolutionized our understanding of solar system. Before Galileo, Copernicus has already proposed that Earth is not the center of the universe, not the center of our solar system. Sun is the center of center of our solar system. And it was very much against the belief that religious powers had in those days. And when Galileo saw this, that there are moons orbiting around Jupiter, it was a very direct confirmation that similar things is happening for Sun, and Sun is having all the planets orbiting around it. So that was the confirmation. That was a change of our understanding of how our own solar system was made of. In 1600s, not far away. Budapest was built in 1800s, right? So only 200s after, or even. So our understanding of this whole thing is so very young and very recent. In 200, 300 years, it changed our own consciousness so much, our own understanding of our own surroundings and our own solar system and the universe. This is really, mind-blowing how much progress we made as humanity. Okay, these are the 4 moons of 4 big moons of Jupiter, approximately size-wise. Io is a very interesting moon. It is the most volcanically active body in our solar system right now. Today, even today, you see a lot of volcanoes from there. And Io is the reason why Europa is totally, charged with that red material. That's because Io's sulfur dioxide goes out, solar wind comes and then ionizes that. And Jupiter is one of the strongest magnetic body in our solar system after the sun. And because of that, in the magnetic fields, all these ions are accelerated so fast to mega electron volts that the ions go and bombard on Europa and other planets. And that's why the surface becomes so red. And Ganymede is one of the biggest moons. Its surface is inundated with craters, you see there. And also Callisto is also inundated with craters. And we don't see that on Europa. That shows that Europa's surface is not as old as our own solar system. Like on our own moon, we see a lot of craters everywhere. Because there are very few craters on Europa's surface, we think that the surface to subsurface exchange happens in the time scale of dinosaurs, lived on Earth, about 60 million years. But still, that is a very short period of time compared to the whole existence of solar system. And that would mean that Europa's surface is actively exchanged to the subsurface. And that is one of the reasons why we think that there is a possibility for us to look into more. Is there? It's okay, you can look at that. Good. So this is the video showing Juno mission. NASA Juno mission went to Jupiter, and it's still there. This is the first time ever we see all the 4 alien moons around Jupiter, and the fastest moving one, this little one, not even in volcanoes. And the next one, and this is Ganymede, and here is Callisto, it's coming slowly. They're all in resonance. This is the first time we could see went onto the polar region, and then the pictures of what we see here. Whereas when we see all of them in line. So I will go. So Europa, what is it? It has some craters, but not many. Its surface is very young, as I said, about 50 to 60 million years. You see this kind of ridges, double ridges and bands. It's very chaotic here on the surface. And you also see tilted iceberg-like things, okay, on the surface. Very few craters again. That means the surface is dynamically changing. And you see this kind of pits, some kind of, volcanism, but cryovolcanism. It's a very, very, very low temperature. So because of all these things, there is a constant exchange between surface and subsurface. And what is the subsurface made of on Europa? If you look into, this is what present models say, is that the subsurface has about 100 kilometers deep ocean with about 10 to 30 kilometers thick ice crust on the top. So ice, ocean, and then below it is rock, and below that is the metallic core. So it is fully fractionated system. And how do we know that there was water? One is that the density of it and the radius of it, all those calculations typically give you estimate of how much is rock, how much is metallic core, and how much is water. This is one thing that very well done for our own Earth and many other bodies in our solar system. We are very well aware of it. But in addition to it, you will see here why Europa is so unique. So I purposefully repeated several things before. So one of the important ways in which we found out that there is liquid water below Europa's surface is through magnetometer that went on Galileo mission. Galileo is the predecessor mission that went to Jupiter and looked at all its moons. These magnetometers are very sensitive, about sensitivity of about 5 nanotesla. And the second thing is Europa's eccentric orbit around Jupiter. That eccentric orbit actually stretches and shrinks Europa up to 30 meters in every 3.5 days. So Europa's rotation around Jupiter is 3.5 days. So there is energy that actually keeps the liquid water. And we know that through magnetometer, there is liquid water. And so the water is there, energy is there. So slowly you see that the conditions are cropping up what life needs. And these are the things that we understood through Galileo mission already. Now Europa is going there to quantify all these things. And the surface is so young, that means subsurface surface exchange is also happening. So all these things put together make it a very, very viable candidate for habitability. So when we want to go to Europa, ideally we could have gone there and orbited around Europa to really find out, or even send something on the surface of Europa, which may happen in a few decades from now. But the biggest problem is the surface of Europa or environment of Europa is extremely radiation harsh. To put it in a context, if we were to be there without any protection, we would not exist within few seconds. So much of radiation there. And even the spacecrafts will not be able to exist there for a longer time. We need, even for Europa Clipper mission, we need highly radiation hard electronics and instruments. You are engineers now, you slowly understand how complex and complicated space missions are. And you will know later on what we did to get this done. But I want to show you who was the discoverer of ocean on Europa. Margaret Kevison, she's almost 100 years old, 94 years, I think. No, 1928. Yeah, about 94, 96 years. So she was the principal investigator of the magnetometer on Galileo mission. And she and her colleagues have found the anomalies in the magnetic fields. And based on that, they calculated that there should be a conducting ocean. That means it should be not pure water, because pure water is not conducting. It should be water with some kind of salts and other things. So that's what is the driver for that. And you have seen this already, that the energy comes from eccentric orbit of Europa. And we know that the density is so much, so we know approximately how much is the ocean, but we still do not know what is the exact nature of the oceans there. And so we have seen that Europa has liquid water, energy, minerals, most likely because there is rock-water interaction, so you can actually have minerals that are needed. Organics could have been either synthesized at the bottom through hydrothermal vents or delivered from comet and other things. And time, I told you in the beginning, time also is needed for life to exist. And Europa, as per today's understanding, has been like that for the last 4 billion years, just like Earth. So all these things put together, Europa is one of the highest candidate for potential habitability of life. And that's the reason why we are going there. And to go there, as I said, it is important to avoid the harsh radiation. I'll show you how it is done. But a flagship mission like Europa Clipper is not done in 1 day or 1 year or 10 years. I'll show you here how much it would take to have such a complex mission to be started and to get the data until it gets the data. So when Galileo mission was there to Jupiter, that was the first time when they found that there was some kind of water or through magnetometer. 1999, a team started defining a special mission to go to Europa. 1999. And it went through so many stages. I don't want you to go through all these things, but it became a mission at one point, and then they said it is not yet mature enough. You have to go back and draw it all the way from the beginning. It is too expensive. So it went back around 2007, and then there was another study done in 2012, and 2014, it started becoming a mission, and 2015, it was officially announced that it will be a flagship mission. So 1999 to 2015, and 2024, we're going to launch it, and it would arrive in 2030. So almost 35 to 40 years of lifetime for one single mission. So it is not one person's pursuit; it is generations pursuit here, and that is the beauty of doing science. Space science it's not my science; it is our science, science of humanity. And we have older people, younger people, middle career people, so that all the information is transferred from one generation to other generation. Okay, so launch is in 2024. What does Europa Clipper spacecraft have? It is here. This is the main spacecraft, and you see this is the magnetometer, and it needs to be far away. It's about, I think, 8.5 meters long. It has to be far enough not to be disturbed by the magnetic fields of all this complex instrumentation here. And then we have solar panels. It's not a nuclear powered spacecraft, solar panels. And on the solar panels, we have radars here. This is high frequency radar and very high frequency radar. All these things can go up to 30 kilometers depth here. And the magnetometer can sense up to 5 nanotesla. I think Europa has about induced magnetic field of about 150 nanotesla, whereas Earth's magnetic field is about 60 or 50 microtesla. And Jupiter is, I think, around 400 microtesla. So that kind of magnetic fields, you need to detect nanotesla accuracy. We have a lot of in situ instruments and remote sensing instruments that I'll show you later. How big is Europa Clipper? So this is the SLS, which is supposed to take humans to moon. That is Statue of Liberty. School buses are very favorite things in America. Every child has to climb into an yellow school bus. That's a unique experience. So everyone understands what a school bus is in America. So sorry, and 6 school buses put together. That's the height of that. And this is the SpaceX Falcon Heavy, which is going to be our Europa Clipper's rocket. And that is Europa Clipper, half of SpaceX, almost like a basketball court. So about 100 feet long, or 30 meters, I think. That's most of it is solar panels. So in order to avoid radiation, in spite of that, it's very high radiation that we are getting. In order to avoid it, what we are doing is, this is Jupiter. We have an eccentric orbit around Jupiter, come closer to Europa, have a quick flyby, and then go away. So as you go away, you get lesser and lesser radiation. And as you come closer, you get more radiation. So this gives us more time to process the data and prepare for the next flyby, rather than sitting here and orbiting around Europa. This way, we're going to do it about 45, 50 rounds. And I'll show you in this next one how this radiation is actually, you see that every time this is the spacecraft, it is not yet in the orbit. Once it gets it there, you see that the radiation is increasing here. And as it orbits, we get more and more accumulation of radiation here. And totally, as we do all these orbits, about 50 of them, we get radiation and then go away, get radiation. That way, we minimize total radiation dose on this spacecraft. And it's about 3 megarad is the radiation dose that we get to the system. It's one of the most challenging and harshest environment ever that any human-made spacecraft is going. Not even, we have some solar probes that are going closer to sun, but not as much of radiation as this one here. So the first one meeting started in 2015. This is the science definition group there. And that is JPL mall. Sophia knows what it's there. And the most recent one happened in Puerto Rico. So after 14 years, we are almost to send the spacecraft. What do we do there on the spacecraft? What kind of equipment is there that needs us to give, that gives us information about the interior structure, surface composition, surface geology, and there are some indications that there are some plumes coming out of Europa. So we need to find out what those things are, and we want to send one day, or whether we or anyone wants to send one day a spacecraft to land on Europa. We want to know what are the best places to land. If we go there, we better know about all those things. So these are the main goals of Europa Clipper Mission. We have a suite of in situ instruments. That means they investigate the environment around them, and a suite of remote sensing instruments. We have a mass spectrometer that looks at gases, another mass spectrometer that looks at dust particles, ice particles, and their composition. And as I told you, magnetometer, which has extremely high sensitivity, that can give us about the magnetic fields and perturbations caused by everything around Europa. And a plasma instrument, by the way, Adrienne is from Hungary. She is a PI of an instrument on Europa. She's at JPL now. The UV spectrometer, 2 cameras, infrared spectrometer. This is thermal imaging. It will give us a very accurate temperature of the surface at various conditions. When it is sunlit, when there is no sun, we have extremely high sensitivity of the thermal imaging camera as well. And finally, radar for remote sensing, and to find out how deep is the ice shell, how thick is the ice shell, and how much is beneath, whether we have water or not. And we will also get from all these things information about the salinity of the ocean. And one more thing is the gravity radio science. They use the K-band of the communication to find out about the gravitational environment of Europa. That gives also us the interior structure. So these are the various flybys that we do. They go everywhere. Almost entire Europa will be scanned. It's almost like a tomography of the whole Europa. And then this is how the launch could happen. Let's see whether it works. Yeah. So SpaceX Falcon Heavy. And then in October, when everything goes well, and then you have the Clipper folded. All the solar panels are folded. And then it gets the wings. It opens the solar panel slowly once it is away from Earth. And let's see where are we now? There it is. It is opening up its solar panel slowly. Not yet. In vacuum, there is no sound, correct? So that's why sometimes there is a proverb called "you're shouting into vacuum." but its silence is beautiful also. So that's where, panels are open. And where are the instruments? You'll see here. You see the magnetometer there, definitely, and you see the radars here. Everything is wrapped into thermal insulation, and this is called nadir deck, and that's where all the remote sensing instruments are there. And perpendicular to that are the in-situ instruments, mass spectrometers, and then of course radio science. You use the antennas there. This is the radar, very high frequency and high frequency radar. Okay, let's see how the flyby happens. This is a simulation, of course. Everything is a simulation until now. So just wanted to give you an idea about how a flyby of Europa Clipper to Europa. With space, you need to have patience also. It's very fast now here on this, but in reality, they're very slow. That is Jupiter. So it's coming from far away and then passing Jupiter by and then comes slowly to Europa. It's getting closer to Europa, and then it changes its orientation so that the nadir deck instruments are looking down and the in-situ instruments are looking in the direction of the flight. And the flyby happens so quickly. And this kind of flybys happen, about 50 of them. And this is how, as instruments were put together, it looks really messy. This is the mass spectrometer that we're talking about. This is the dust analyzer, and that is the nadir deck where we have all the instruments. This is done in a very high clean room. We don't want any dust and anything else to be there. And these are the solar panels. One wing actually is this one. And then this is very recently, after it was put it in a vacuum chamber and exactly simulated the conditions that it would see as it is in the space, and it passed all the tests. It is called TVAC, very, very important critical test. There are hundreds and thousands, probably, or even tens of thousands of tests that we do to ensure that the spacecraft is able to do what it is supposed to do. Even then, there could be troubles that come. And you can never be out of troubles when you have such a complex mission. On the right side, you see that everything is now wrapped up. It is called MLI, that is the multi-layer insulation that protects from radiation and also thermal environment outside. So some of the instruments are heated internally. And so this is the procedure that's done. Once it is very soon, before I go back to JPL, this will be gone. This will be airlifted to Kennedy Space Center. And there it gets the solar panels mounted with resin antennas and folded and then put onto spacecraft. Around the same time, okay, this is about how we're going to do. We're going to launch October sometime, and it's going to have a Mars gravity assisted, and then come back and take also some more energy from Earth, another Earth gravity assist, and then take off, go to Jupiter in March 2030. Okay, so in about 6 years from now, it's going to be there. And interestingly, about the same time, ESA has another spacecraft. It's called JUICE. It is going to look at Ganymede. We have 4 Galilean moons: Io, Europa, Ganymede, and Callisto. So this JUICE mission is going to look at Ganymede, and it was already launched. But they're going to be at Jupiter around the same time. And in fact, a couple of times they'll be so close to each other, and they're thinking of actually using their cameras to see whether the other spacecraft is there or not. Okay, think about this. About 5 AU from the sun, 4 AU from Earth. 1 AU is 150 million kilometers. So about 1 billion kilometers away. We are doing something that is so spectacular and so unique. It's really, mind-blowing. They're going to be the same time. You see that they cross, and then sometimes they go in parallel with each other. So this is going to be a very exciting time in 2030s. Okay. So I just want to stop and show you. This is Claudia Alexander. She was the project scientist for Galileo mission. And then she was project scientist for ESA, NASA, Rosetta mission. And I worked on Rosetta mission with her. She expired, I think, sometime in 2012 or something like that. But it shows that, these kind of endeavors are generational. Okay, she started that Galileo mission, and then she was involved in Europa definition, and she was with Rosetta, and now we are taking it forward. Okay, she was a wonderful person. I just wanted to, pay tribute to her. Such a wonderful person. Okay, it's a big if. Okay, if there is life. And that's what what we're going to do is the first step. We are not going to find life there. We're going to find its conditions, whether how endurable, how facilitating those conditions are. That's called habitability. But as you have seen, this is not only science, this is an enormous amount of instrumentation involved, remote sensing and the in-situ instrumentation. Each instrument has a heritage of probably 30, 40, 50 years, okay? And so we have to keep all those things in mind. Now I'll come to the last part of the talk. This is more about combining everything into also human touch, give a human touch to the science endeavor. We have started this campaign called the Message in the Bottle. Throughout the world, this was a big campaign. Everyone could give their name, and we had about 2.6 million names. And all those names, in fact, I actually gave a name of one of our colleagues in Europe, in Holland, who suddenly died. To pay tribute to him, I put his name also on that. So they're going to be engraved in, they are already engraved in a microchip that is going to be connected to the vault cover. So this is the cover that is going to be put on the spacecraft after everything is done. All the red tags are removed. Everything is ready to put it into the rocket and ready to launch. And at that time, they also close this vault. And that vault plate is a very important thing that I'll show you in the next slide. It has, like if you remember, Voyagers have a message. I think it's in the Voyager. Isn't it Voyager or Galileo? Well, no, Voyager has the golden record, if anyone remembers that, okay? That also shows if somewhere in the future, if some intelligence were to be able to see this, they would understand it came from Earth and there was intelligence at that time, okay? And whether we continue to be intelligent in the coming, thousands of years, we don't know, but that gives an impression. Here we have a poem by US poet laureate Ada Limon, In Price of Mystery. And then we have a Drake equation here that gives us the probability of finding communicable intelligence in our galaxy. One day we may be able to communicate. And this is actually the Jovian Galilean moons here. This is sort of Jupiter here. And Ron Greeley is one of the leading, he was one of the leading planetary scientists who was strong supporter of Europa mission to Europa. He also died in around the same time, around 2010, 2010-ish. And here on the back side, no, this is the front side actually, this is the back side. Front side, waveforms of water spoken in about 104 languages on Earth. So this is something that actually symbolizes that we are connecting water from Earth to Europa, and that our humanity is connected to that planet, I'm sorry, to that moon. And unfortunately, if it goes according to plan, Europa Clipper will be crashed into Ganymede. So what happens to this doesn't matter, but it's like, and here is the poem from Ada Limon. It's beautiful. So that's the end. But one thing I want to convey is this kind of missions and the science we do bring people together, bring cultures together, bring continents together, make us one humanity. And this is so beautiful doing science and technology, what we do, that is bringing every one of us together to achieve something much, much, much bigger than any one of us could ever dream of. And that is the beauty of doing space sciences, exploring beyond thinkable. And as it is said by Charles Elachi, our previous director, dare mighty things together. Thank you so much. And we have a Europa. Yeah. Thank you.
Questions from the audience, and if there are questions online, please share with us your thoughts, please.
This one, a rather philosophical question. Well, how do you define life? Looking for life.
That's a very, very, very deep question, very philosophical as well as practical. Right now, you cannot open the parameter space to beyond life on Earth. If we open the parameter space, we are lost because there could be so much more there. But according to our definition right now, what we are looking for elsewhere is Earth-like life, whether it is a single cell bacterium or microbes or archaea or anything onto multicellular or whatever it is. The carbon-based, water-based, mineral-based life. There are people who are working on other forms of life containing other backbones containing elements other than carbon. There are some people who think that silicon could be. But if you look into, there are so many important things that are critical for life. It's more likely it should be carbon-based because it should be flexible, at the same time rigid. It cannot be rigid only. And similarly, water is such a unique system. It has the dipole moment. So life needs electrical gradients, and dipole liquids enable electric gradients. So as much as I think what we are looking for right now is life like on Earth. But the rest of it is open. If we cannot find this, then we are searching for something that we do not know what we are searching for. That is the philosophical question. Hope I answered your question.
As far as you can.
Yeah. So if you can define what else could be life, then we can search for it. But if we cannot define, it's like, I don't know what I'm searching for is not scientifically possible. Philosophically, it is definitely possible.
Any other questions, please?
How can we make sure that the magnetic effects are always the
the magnetic field, first of all, that's a very good question, excellent question. The magnetic fields, if it is like Earth's fluidic metal core, Okay, it cannot be rigid because the magnetic moments have to be aligned. Otherwise, it's not, randomly aligned magnetic fields do not work. If it is fluid, the present models say that Europa doesn't have that much of energy to keep the core hot. It has just enough energy through the friction to keep water liquid in certain parts. And that is the reason why we think that anywhere else, you need these aligned magnetic fields, which is not there. That's what we think. Yeah.
So last time I checked, I knew also there was a model of Europa containing more amount, not just this thin layer of water. So have you ruled it out?
About 100 kilometers is ish. 100, probably 200. See, when we say it is approximately 50% uncertainty, and we want to constrain it even more. The problem is, I don't think that Europa Clipper Mission will constrain the thickness of water, because radar, recent radar can only go up to 30, but we can constrain the thickness of ice. Okay, and below that, how deep is the ocean? We don't exactly know. It is the present models. These models are not that bad because they are geological models, and they have been tested on Earth and many other bodies. And make it with a slight amount of error, whether it is 100, 150, 200. If it is, the radius is 1500 kilometers, 100 or 150 or 200, it doesn't matter. But it cannot be 500, because if it is 500, then we cannot get the density correct. And you also have, everything else associated with it. That's why I think it's more or less, yes. Yeah.
Does this spacecraft have the sort of traditional engine thruster with the liquid fuel and stuff?
Yes.
Doesn't really have some of the exotic thrusters?
No exotic thing here. No, it has normal thrusters. Yeah, I think hydrogen or something like that. Yeah, we have. That's one of the reasons why we have to be careful not to contaminate the mass spectrometers and other things, because it could be false detection of something that is nitrogen based and things like that. Yeah. We have solar panels and we have normal thrusters. Yeah. It takes a lot of time before you get those things on spacecrafts. Yeah. Yes, it's going on. What you do is, when you do flagship missions, you don't put newest technology on that, because you want to make sure that you have least possible single point failures. Yeah. Yeah.
I noticed the issue about the beginning, you mentioned the fact as well, and it having the from the surface. Is that for sure?
Which one? Oh, so by the way, none of solar system bodies have liquid water on the surface except Earth. Mars has ice, as you know, polar caps. Titan, Europa, and Enceladus, Ganymede, all of them have liquid water within the ice shell. Okay, because of fractionation, because of the density, we know that there's so much of water because of temperature gradient. There should be somewhere temperatures that are, 270, 80 Kelvin, and that's how they model that there is water. But Titan has surface lakes. Exactly. it's made of methane because A, Titan has an atmosphere that's 1.5 times of Earth's atmosphere, and B, surface temperature is about 90-ish Kelvin. That's the temperature, that's the pressure where methane and ethane are liquid. And so you have beautiful lakes on Titan. Yeah.
For Europa, you mentioned some basics about the water physics conditions, the water temperature, and what about the soil? What about the soil of?
So we said rock.
Yeah,
Rock is again according to models, we should have rocky core about 150 kilometers below the surface. Yeah, and that is the place where water is liquid, and the rock is like olivine and any kind of the whole solar system has this kind of rocky material that comes from interstellar icy grains and minerals. And the same kind of rocky grains are there. They are now fractionated. That means they're all compressed inside. And they are in interaction with the liquid at probably at anywhere between 0 Celsius to 30, 40, 50, 60 Celsius, or even 100. We don't know. And that is where probably a lot of hydrothermal vents could have been there, or that kind of rock interaction could also make catalytically some chemistry there.
What about the surface soil?
Surface is completely ice, water ice, up to 30 kilometers, 10 to 30 kilometers. Oh,
so we imagine that there will be a life on it. How could this life activity be only on water?
It's in the water.
Inside
Yeah, it's almost like diving deep into, let's say, 5-10 kilometers deep water, and the life that we see there could be the life that is existing there, and it will never see sunlight. Okay. But you don't need sunlight because you need other form of energy. Yeah, and so that's what is our hope. If they're on the surface, they would die within no time. There's so much of harsh radiation there. Yeah.
Any other question from the audience?
Philosophical?
So maybe I have a last question, and then if you are still having some time, Dr. Gudipati is going to be here, so we can approach him unofficially.
Yeah.
Just asking some questions. So my question would be, so we heard that there will be 50 flybys, but what is the lifespan of the spacecraft? So from the time that it arrives to Jupiter.
So we have about 3 years.
3 years.
Of the primary mission. And if everything goes well, if it is delivering science, and if there is no unexpected radiation related damage, we could extend it for another year or two. So 3 to 5 years. Sort of slightly optimistic, 3 years. More optimistic, 5 years. Pessimistic, I don't want to say. We are not pessimists.
Okay.
Yeah.
So with this question, we are closing this session. Thank you very much for coming. And Mr. Gudipati is still here. Please feel free to reach out to him. And thank you very much for those people watching online. Thank you.